Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and or questions, drop them in the comment section below or write to us, info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
All right. Hello, everyone, and thank you for joining us today. Let me welcome you to our today's webinar brought to you by Oxygen Alliance. My name is Victor Mbembe, and I'm a permission engineer with Oxygen Alliance. I'm joining this talk from Malawi, and I'm excited to be your host today. So in our today's session, we are focused on the technical repairs and troubleshooting of patient monitors. And this webinar would be led by biomedical engineers from the Oxygen Alliance and Open too. So as for the presenters, we have Kelvin Saidi with the technical support officer for the Oxygen Alliance. We also have David Noah, who is the information engineer with the Oxygen Alliance. And lastly, we have Dominic Mapanje, who is the information engineer with the Open too. So just to let you know, after the first two presenters, we will take a break for questions, for comments, for 2 or 3 questions, comments, and then our final presenter. Otherwise, without wasting much of your time, I want to hand the floor to Kelvin Saidi. Let us do the first part of the presentation. Thank you.
Thank you, Victor. Once again, my name is Kelvin Saidi, and I'm a biomedical engineer with the Oxygen Alliance. And this presentation, I'll be joined by my colleagues, David Noah and Dominic Mapanje. So this webinar will talk about the technical repairs and troubleshooting of patient monitors. So the outline for this presentation, we'll first talk about patient monitors and their accessories. We'll look at the key device components externally and internally. We'll then talk about the overview of the working principle. We'll then move on to preventive maintenance, performance testing and verification, some common faults and how to repair them. And we'll also take you through the troubleshooting technique or process. So what are patient monitors? So these are devices that are used to measure a patient's vitals, such as their temperature, SpO2, the blood pressure, heart rates, and ECG. So these devices, they're important for continuous observation of physiological parameters. They also enable immediate clinical intervention. Since the monitoring is continuous, the nurses or the doctors can jump in whenever necessary. So on your right, you can see a typical patient monitor with its device accessories. So you can see we have a screen right here. We have the BP cuff. We have some sensors, an ECG lead, and a power cable. So these are just some accessories that come with a typical patient monitor. Let us now look at the types of patient monitors. So patient monitors are classified into different types based on 2 main lessons. So the first one is how they are physically built, or the modularity, or where they are clinically used, or the application. So when you talk about the modularity, we have the modular patient monitors and the integrated patient monitor. So for integrated patient monitors, these are single self-contained units, and all the measuring, the electronics is built into the main box, the main display, and they have fixed ports for standard vitals. So you cannot add new capabilities later, whereby a modular monitor acts as a host for swappable mini computers that are called modules. If you look at the picture, on the bottom left, you have a modular patient monitor, and you can see that that is an example of how these modules look like. So these modular monitors, they allow clinicians to slide in specialized modules for advanced vitals, such as brain function or anesthetic gas analysis. So this is done as the patient's condition become more complex. If we look at how patient monitors are classified by application, you have the portable patient monitor and the bedside patient monitor. So Bedside or stationary patient monitors are heavy-duty devices, and they're used for continuous monitoring in a fixed place like an ICU. Whereas the transport patient monitors, these are used or they are designed in a rugged way, and they are mostly battery-powered units that stay with the patient in transit when maybe the patient is moving in between departments or the patient is in an ambulance. So this ensures that there's no gap in the data collection. So one thing to note, it is important to note that these categories can overlap. What I mean by this is that a monitor can be modular in design while also serving as a bedside unit. So it is important to note that as well. Let us now look at the key external components. So this is a well-labeled of a patient monitor. The main components are the display, which uses a high resolution TFT LCD display, and this can clearly show the physiological parameters and waves and other information of the patient. So as you can see in the picture here, this display is, you have an alarm indicator area here. You have the wave area here where your ECG wave is shown. Here you have the parameter values, the SpO2, you have the SpO2, the heart rate, and then the non-invasive blood pressure measurement right here. So if you look at the diagram, we also have some buttons below the patient monitor. You have the power button, you have the AC and battery indicator. So these ones tell you what the machine is running on at that particular time. We have the alarm silence key, the NIBP measurement start or stop key, and you have this control knob that can be rotated to the focus or to move the focus when pressed, or to access some menu options or execute a command. These two buttons here, one is for the freeze function. So when you freeze a patient monitor, if it is showing a wave, an ECG wave, that ECG wave will remain stationary for easier interpretation by the doctors or the nurses. Whereas the print key function, you just print that particular wave for further appreciation on a hard copy paper. So let us now look at the patient interface module. So this is where all the sensors and leads are connected from the patient side to the device for processing and displaying. As I was saying, they consist of well-labeled ports for each parameter that the monitor can support. So from this image here, you can see it is well-labeled ECG, temperature, T1 and T2, SpO2, and NIBP. So some of these ports have arrows, which should match the probe or lead that is going in that port, so that there should not be a mismatch, and which can result into wrong results. So these arrows, they help the users to easily install the probes and the leads. And then moving on, we have the network interface module. So this is used for communication between the monitor and other devices like laptops. So it can support various network protocols, such as the local area network, serial communication, and HDMI. Now, let us appreciate how patient monitors look internally. So this is how a patient monitor looks internally when you've just opened it up. So you can see we have the PCB that has small ports that are mounted on it. We'll talk more about that as we go on through the presentation. We have the BP pump and then the NIBP signal acquisition module. We have the speaker. So we'll talk more about this as we go on. Let us now look at the power supply. Most monitors operate on 100 to 200 watts AC mains power supply. Yeah, so they also have an internal lithium-ion battery, and in the case where there is no mains power supply, there's an automatic switchover for uninterrupted monitoring. So the picture on your right, you have the battery that is used as a backup, and this power supply board. So as I was saying, this is how some power supply modules look like. So you have the battery and the main board that receives the main supply and processes it, steps it down, and then sends it to other boards on the device. Let's now look at the SPO2 module. So its main function is to capture raw biosignals in the form of light on the finger probe. So the picture here shows you a typical SPO2 module. So this is the connection where the signals are transmitted to the board, and then the components on the board do the filtering, the amplification, and then send it to the main board for processing. We then have the non-invasive blood pressure module, and this one also captures raw signals in the form of pressure. So this one is a little bit more mechanical in such a way that it controls the pump to inflate the BP cuff. And then we have these pressure sensors here that take the pressure changes as the cuff is being deflated. And then those signals are then sent, they're then amplified, filtered, and then sent to the main PCB board for processing. Now we have the main control board. So its main function is to process the acquired signals and convert them into actionable information. It also controls the LCD, speaker, and all other modules on the device. Let us look now at the alarm system and the logic of these patient monitors. Alarms can be classified into two parts. You have physiological alarms and technical alarms. So physiological alarms, these are alarms that sound when patients' vitals cross a certain threshold. So maybe, for example, if the SPO2 is below 90%, these alarms will be generated. Whereas technical alarms, these are system issues. For example, leads off or the battery is low. So these alarms will also be generated. Most patient monitors have a latching safety software feature. It's a feature that keeps an alarm going even after a patient's vitals have reached normal. This ensures that if a nurse is away and misses a short-lived event, like a quick heart problem or a sudden drop in oxygen, the monitor will still be alarming when they return. So this forces that the staff check the monitor's history and see exactly what happened and when. So by keeping these temporary problems visible, this latching helps the medical team see the full history of the patient's health so that they can make best treatment choices. So the picture below here, you have an alarm section. This section is for the physiological alarms, and this section, the technical alarms. It is also important to note that this can change according to the patient monitor you are using. Now, let us look at the overview of the whole working principle of the patient monitor. So it can be categorized in four main groups. You have the sense, acquire, process, display. And after display, you can alert or then store. So on the sensory part, we are capturing raw signals collected via the patient interface module. So it is collected by using the ECG reads, the NIBP cuffs, the SPO2 probe, and the temperature sensor here. So once these signals are collected, they are then to transfer to their prospective signal acquisition modules, where they are filtered, they are amplified, and then sent to the main CPU for processing. So the CPU is equipped with algorithms that turn these signals into actionable information. And then after this is done, the CPU then also sends signals to the LCD to display ECG waveforms and some parameter values. If a certain threshold has been reached, an alarm will sound to alert the user that there is a problem. And last but not least, this information can also be stored on compatible devices for further analysis. Moving on, let us look at the planned preventive maintenance. And on this section, my colleague, David Noah, will take you through this. Thank you, everyone. And over to you, David.
Thank you, Kelvin. And my name is David Noah, a biomedical engineer with the Oxygen Alliance. I'll take you through the next part of the presentation, which is the planned preventive maintenance. So planned preventive maintenance is one of the most important responsibilities of the maintenance personnel in hospitals, especially for patient monitors, because these monitors are continuously used in critical care environments. For example, the ICUs, we have the theaters and HDUs. So basically, in patient monitors, planned preventive maintenance involves routine inspection of cables and accessories, cleaning and infection control, function testing of monitoring modules like the ECG, the SpO2, and the non-invasive blood pressure, alarm testing and performance verification, and last but not least, the electrical safety verification. So to begin with, let us look at a bit of detail at each and every aspect of the preventive maintenance. So the first one is the routine inspection of cables and accessories. So this one is also an important aspect of the preventive maintenance. So because patient monitors rely heavily on accessories, and these accessories are continuously handled in patient care, and hence they are susceptible to some damages. So on a daily basis, maintenance personnel or the clinicians should do visual inspection, which will involve checking the ECG lead wires for cracks or exposed wires, checking the SpO2 probes and NIB cuffs, and even the power cables for any kind of damages. You also have to ensure that the connectors are secure. So you can see from the picture that the cables are exposed and most of them are badly damaged. So this is mainly because of poor handling of these cables, which happens in different facilities. So in the long run, you also have to make sure that clinicians and the users of these cables are trained on how properly to handle these cables. Because in the end, these damaged cables might affect the signal artifacts, or in some cases, make the complete signal loss, which might in turn affect the clinical decision making. Weekly or monthly detailed inspection should involve examining the pins for corrosion or bending and inspecting strain relief points, which are those points which faces repeated bending, which might be damaged. So you should make sure that those points are not damaged and that the pins are free of any kind of corrosion or bend. Moving on, let us look at another aspect of preventive maintenance, which is cleaning and infection control. So patient monitors, as I said, continuously used in critical care environments, and they are connected directly to patients. As such, these things need to be infection free and have to be cleaned either daily or so daily cleaning should be performed using a recommended cleaning solutions. So commonly we have the 70% isopropyl alcohol or ethanol, or sometimes isopropanol wipes. Another important disinfectant is the hospital-approved disinfectant wipes, and also mild detergent solution with soft cloth. So casings, display leads, and SpO2 probes, plus the BB cuffs, should be cleaned of any dirt to remove the contamination, which might come from either the patient or vent. Weekly maintenance or monthly maintenance should involve a deep cleaning, which, among other things, involve removing the dust from the ventilation openings to reduce overheating. You also have to inspect connectors and ports for any kind of contamination and remove such contaminations and clean usable sensors according to manufacturer's instructions. So during cleaning, some of the precautions that have to be followed include not using the harsh chemicals like the bleach or strong solvents, because these chemicals might end up damaging the plastic casing of your patient monitor. And also make sure that excessive fluids are not allowed to enter the connectors or the ventilation openings, as this might cause some shootings inside the patient monitor. So moving on, another important aspect of preventive maintenance is functional testing of monitoring modules. So basically, this is performed to confirm that the patient monitor module is operational and responsive, and this should be done either weekly or monthly. So to do these tests, you simply connect the probes to the monitor and check if you are checking for the SpO2, for example. You simply connect the SpO2 probes to the monitor and check if it's able to display the SpO2 values on the monitor. And for the NIPP module as well, you simply apply the cuff to the patient monitor and check if the monitor is able to inflate or deflate the PP cuff. And for the ECG, you simply connect the leads and check if the monitor is able to display the waveforms and calculate the heart rate. Another important aspect of the planned preventive maintenance is the performance verification. So basically, in this case, you are trying to ensure that the modules are providing accurate readings on the patient monitor. So it ensures accurate monitoring and safe operation after installation or maintenance and sometimes repair. So this should be done using biomedical test equipment such as SIMS. So it should be noted that there are some specific simulators for specific modules. For example, the SpO2 simulators, the NIPP simulators, and there are also some multi-parameter simulators which you can use for all the parameters. Generally, what you do is you connect the monitor to the appropriate simulator. If you're using the specific simulators for the specific parameters, for example, for SpO2, you have to connect the SpO2 simulator to the monitor and then set the simulator to a nice value. So if you are trying to measure or to verify the performance of SpO2 module, you have to set SpO2 at something around 98%. And then you compare the value displayed on the monitor with the simulator value. After that, you confirm the reading with that it is within the acceptable tolerance specified by the manufacturer. From the information on the simulators and how they are used, you can go to our previous webinar that we had. The link will be pasted in the chat. Another important aspect in as far as preventive maintenance is concerned is that of electrical certification. So electrical safety verification in patient monitors basically should be conducted annually. So patient monitors are devices which are connected directly to patients, and at all costs, it is important to make sure that they do not pose any hazards. So it is important to conduct electrical safety so that we protect both the patient and the user. So electrical safety testing, basically we measure the leakage current using the electrical analyzer. So you can see in the image, the electrical safety analyzer, which is used to measure the leakage current, the grounding resistance, insulation integrity, and this ensures that the monitor does not pose electrical hazards to patients or stuff. Moving on, we have the alarm testing as also another important aspect in as far as preventive maintenance is concerned. So alarms and patient monitors are lifesavers because they are the ones that inform the clinicians when the physiological parameters fall outside the safe. So it is always important to make sure that these alarms are audible enough to be heard by the clinicians so that they can act accordingly on the physiological parameters that have discrepancies. So daily alarm testing should involve making sure that the alarms are audible enough to be heard by the clinicians and that they are able to be displayed on the screen so that the clinicians are able to see them as well. On the picture there, we have a section where the alarms are displayed. So basically, the alarm section is somewhere here. And then here, weekly or monthly alarm testing should involve making sure that the alarm limits are set on the monitor. For example, to test the limit, to test the alarms, weekly or monthly. First of all, you have to configure alarm limits on the monitor. For example, heart rate, you can set it at a maximum of 120 beats per minute, and then a minimum of 50 beats. And then you use the simulator to generate values outside these limits. For example, you can generate any value less than 50 and check if there's any audible alarm or if there's any indicator on the alarm section that the heart rate is too. You can also try to generate a value that is greater than 120 beats per minute to check if the monitor will display something like the heart rate is too high, and if there will be any audible. So basically, you confirm that the monitor activates alarms, display visual alarm indicators, and show correct alarm messages on the display. So before moving on to the next section, I'll hand it over to the host, Victor Nzembe, for any comments and questions. Over to you, Victor.
Thank you so much, Kelvin and Davis, for that wonderful presentation. So at this moment, like this, we're going to take. So for the meantime, I'll just take 2 questions from the chat, and then after that, the rest of the questions. So I hope everyone understands that. So there are a lot of questions in the chat. I'll start with a question from David. You asked if there is a procedure. What is the procedure for protect the notification for the patient monitors? What is the procedure for the protected notification for the monitors? I know that the presenters are saying something about the use of monitors. I don't know if that answers your question or if you need more clarity on that. So, David, if you need more clarity, just give me a thumbs up. Or if not, then if I move on to the next question. All right. There was also a question from, is it Kelvin? I don't know if I'm pronouncing the name correctly. Was asking, how can we implement a functional test on the SO2 sensor? How can we implement a functional test on the SO2 sensor? So maybe David can just come in on that again. I know you are the one.
Victor, can you please repeat the question?
So the question is, how can we implement a functional test on the SO2 sensor? I say I'm Janet. It can come in.
All right, thank you. I hope you can hear me. I'm a biomedical engineer with Oxygen Alliance. I'll just take some of the questions. Let me start with the verification of the SPO2. Normally, for you to verify the functionality of the sensor, you use a simulator. That's the most recommended one, in as much as David had explained that you can just try to see if you're able to see the results. You put in your finger, you see the results. That's like the basic functional testing that we are supposed to be doing, because normally when the nurses are using this equipment, they don't do checks. They just, as long as they're seeing your readings, for them it's okay. They would even think that it's because of the patient why they're seeing, let's say, lower values than expected. So for you to really verify if the results that are being shown on the monitor are correct or not, you're supposed to use the patient data. And on the simulation, David had area explained how you go about it. You set the values on your simulator. The simulator has a connection point where you can connect the sensor from the patient monitor to the simulator. And then it makes sure that the values that you're seeing on the monitor should be the same as the one that are being seen on the simulator. If the values are not the same, then definitely has to be that either the probe or there's any other issues with the connection to the patient. There was also another question about the testing of electrical safety. But normally, as David was explaining, he mentioned about the leakage current and the like. For you to do this, you use the electrical safety analyzer. The analyzer, normally, if you have access to an analyzer, it comes with its manual where it explains what you're supposed to do. But I'll just say in brief, normally you're supposed to also check the class of your device that you're measuring. If you're looking at leakage current, we measure the points of contact between the device and the patient. Any point where there can be transition of current, that's where you're supposed to connect your analyzer. But otherwise, every analyzer has specific processes that you're supposed to follow when you're using the analyzer to measure either the leakage current or else the voltages itself. Because there are so many tests that you have to do based on the ISO standards that are there.
All right. Thank you so much, Janet, for that explanation. As I said, I've taken some questions to the chat to bear with me. The list of the questions will be taken at the end. It's not like we are going to skip them. Right now, I will just take a hand from, I think it's IQ, if I'm pronouncing the name correctly. You have had your hand raised for quite some time now. So if you have something to ask, you can speak. Oh, I've seen that you have lowered your hand now. With that, and I think we can continue to the next part of the presentation. So, and this the rapid event with Dominic Mapanje.
Yeah, sure. So I'm Dominic Mapanje. I'm a program officer for OpenO2. So I'll be taking you through the common faults that are found with the patient monitors and also how we can troubleshoot these common faults. So before we jump into those faults, we should just talk about the troubleshooting approach that we as technicians or engineers should be taking. So firstly, for a technician, it is always recommended that they should follow a structured troubleshooting process. So what does this structured troubleshooting process look like? So you should actually start with the accessories, so external accessories, and then go into the internal components. So you are starting from the external, going into the internal parts. So effective troubleshooting requires a systematic approach, beginning with the simplest external checks before moving to internal components. So you are basically checking the accessories. So it is estimated that 70% of monitor ports actually originate from accessories.
Sorry to cut you, Dominic. You just please turn on your camera for a moment.
Oh, sorry.
And then after 10 minutes. Thank you.
So yeah, I'm Dominic. So I'll just proceed from where I left. So we are talking about the systematic approach that engineers will actually be taking. Engineers or technicians will actually be taking on troubleshooting. Of course, not only monitors, but all other equipment that you are troubleshooting. So you mostly start with the easy parts. So for a monitor, you are actually starting with the external accessories and then going into the internal components. So we have said that it is estimated that 70% of the monitor ports actually do originate from the accessories and not the monitor itself. So it is important that you first check the sensors and the accessories. And then from there, you can go on to check the monitor settings. Because sometimes it's the incorrect settings that can produce the errors that you are actually seeing on your monitor. So let's say you have set your settings for a neonate, and then you are monitoring the parameters and others. So you should expect there will be some errors there. So the next step is the use of simulators. I think that I can talk much about. It helps you to isolate the ports. Is it the monitor itself or is it the external accessories. And then lastly, you then go into the internal components. So you take the connectors inside, the internal connectors, the modules, and the motherboard itself. So that is if the program is it. So you then go into you go on to discuss among it. So in most hospitals, these are some of the technical reports. This is how the technical reports actually do look like. So I've said that the external accessories make up to around 70% of the reports, and then the NIPT pneumatic components make up to 20%, 15 to 20%. The power system, that is the battery and the power supply, make up to 10 to 15% of the faults. And then the internal electronics make up to 10%. So it's advisable that you start with the most common found faults, so which are the external accessories and probes, before you go into the less than 10% of the faults that are actually do happen. So that is disassembly. So start with the easel, part of the troubleshooting, then you go in there. And then these are some of the common faults that actually do happen. We have damaged probe wires or worn lead wires. So this actually do occur because of the mechanical stress that do happen with the wires. So you can have internal conductor breakage and also intermittent open circuits. So it happens that you move a little of the axle, it works, you move it a little bit, it doesn't, so something like that. So you know that there's some kind of open circuit inside the your in your accessory, in your probe. So another thing is cable insulation damage. So as you can see in the picture here, so we have the probe which has a worn out jacket. So wires are exposed. I think you can see clearly, and you can see that the internal wires are actually exposed. So this is another common fault or another common failure mode. And on the right hand side there, we have a pin with bent, a connector to bent pins. So that's another common fault that we actually do find in the hospitals. So this actually causes an intermittent signal loss. It can cause noise ECG waves or ECG lead wires, and it can also show that the parameters are not being detected. So how we can actually troubleshoot this is to perform a visual inspection. So with visual inspection, you can actually see that, oh, the pins are bent, or you can actually see that the external jacket of the probe is worn out. You can also perform a weak test. So you would go your probe to see if there's any weak points. Of course, this is not really reliable, but sometimes it can actually work. You can use it to see where there are breakages in your internal wires of the probe. So another best way is actually to just substitute with the non-good probe or sensor. So you know that if you have replaced it and it is working, that means the other one has a problem. And also you can verify using a simulator. And going on, we have probe sensor failure. So for probe sensor failure, that probe or sensor failure that can be CO2 probes or ECG reads or temperature probes. It can also be CO2 probes. So for CO2 probes, mostly you find that the LED emitter, you cannot see the LED lights. So the LED emits the LED lights, so you cannot see it. You cannot see any lights here. So you know that there's a problem. So we can use a photodetector that actually detects the light that is being emitted. So it can be barium gas. It can be that the optical window, that means the sensors are actually contaminated. And for ECG electrodes, you can see high electrode impedance. So that's the resistance between the patient's skin and also the ECG electrode. So for actually ECG acquisition, this impedance must be low and stable. So the small cardiac electrical signals can be detected properly. So if there's any kind of impedance, this can be because of sweat, can be because of skin or oils on your, hair or skin or oils on your skin. So this can cause high electrical impedance. So that can cause high resistance between the electrode itself and the skin. And can be oxidized connectors. That means that some kind of blackness formed on the connectors. or it can be poor contact due to dried electrodes. So the gel that you put on the electrodes can be that it is dried out, so there's poor contact. For temperature probes, it can be a thermistor drift. So we know that most medical temperature probes actually use a thermistor, which is a resistor, whose resistance changes with temperature. So thermistor drifts actually do occur when the resistance to temperature relationship changes over time. So that can be the cause of the failure with the temperature probes. It can be the broken sensor wires or connector damage as well. So for connector damages can happen for all these probes or sensors. It's probes, CCTVs, temperature probes, or the CO2, carbon dioxide probe. So how do you troubleshoot this? You test it a not good probe. So we have said that is actually a good way of doing it. Testing a good spot, so you know that the probe which was there, which was not working, has actually the problem. It's not the monitor itself. So you inspect the connector cables and the strain points if there are any strain points, and then you can also verify if it is stimulated. And another common thing is common faults, the air leaks in the NIDD system. I think this is most the common thing with the NIDD system in monitors, or even the BD, the small BD machines that we actually do find in hospitals. So there are typical leak points that I can actually check. So you can deal with the cap bladder itself. I don't know if you can see where I'm pointing at, where I annotated in the picture. So that's where most of the leaks do happen. And it can also be cracks in the pipe itself, in the tubing itself, or in the connector points here. I hope you can actually see those annotated points. So that's where the most leakages do happen. For this, you actually have to see that there's slow inflation in your cups or measurement has been aborted. It also does 10 years on the monitor that the loose cup. It can be inaccurate pressure readings. So it does put inaccurate pressure readings. So how do you troubleshoot these things? You have to pressure inspect your car for any cracks, and then you test for any leakages. So you can perform a pressure leak test. So on the monitor, there are settings on some monitors. I think, anyway, it's not all, but then on most monitors, there are actual settings where you can do a pressure test. So it does on its own, it measures the pressure that is being produced, and that is really indeed the pressure that is being produced. So it knows, the monitor knows that there is some kind of leakage. So another thing that you can do is actually the PP cap. So on the monitor, you connect the PP cap, you start the NIDD. As it is inflating, you squeeze it. So if there's some air being leaked out, going out of the cap, so you know that there's some kind of leakage there. Now, from there, you can actually start checking where is it, the air leaking. So another thing, you can just, after you found the leakages, then you replace the damaged tank. Or where there is the tubing, you do replace it. Another common fault in the NIDD system is the NIDD dump failure. I think this is also common. Yeah, it is very common. We actually do find it in the hospitals. So this can be caused by the one diaphragm. So in the diaphragm pump can say that the diaphragm itself is actually worn out. It can be motor failures that the motor is not working anymore. So it's not it's actually not pumping anymore. It can be mechanical blockage. So it's a mechanical thing, so it can be actually blocked somewhere. For this also, you will see that the cap is not inflating, so you can actually suspect maybe there's something with the pump itself, or there's slow impression, or there's actually measurement failure we can avoid it. So you can suspect. So you have gone from the external cap itself, the tubing, the external tubings, and then you're going inside. You can now start checking the pump. Is it the pump itself? So how to troubleshoot for this? You actually listen to the pump operation. So if it is, you can actually hear it in most monitors. You can actually hear it in operation. You can also measure pump supply voltage. So is any power going to the pump? So is it with the pump or is it with the electrical system going to the pump? You can also check for the pneumatic part blockage. So you check, is it some kind of blockage just after the pump that air is not going to the caps. And then if you find that there's a problem with the pump, then you can actually fix it. Now we also have the valve failure and also pressure sensor failure. So for the valves, you can see that they are stuck or there's some kind of leakage, especially on the connectors. So if you see the picture down here, we have valves, these small valves, 2 of them. So you can see that they're stuck or that they are actually, or there's some kind of leakage. So with the sensors on your right side, there's the actual sensor, pressure sensors. So you can see that there's a pressure sensor drift. So this occurs when sensor output slowly changes over time. So even if the actual pressure remains the same, but you see that the pressure output by the sensor is actually different from the actual sensor. So it has changed, it has deviated from the actual sensor. So you know that there's actually a pressure sensor drift, or it can be electrical connection failure, especially with valves. So the symptoms of this are that pressure not being released. So if the valves are not working, pressure in the cup may not be released, or there can be incorrect pressure, incorrect blood pressure readings, especially with the when there's a fault with the pressure sensors. And how to troubleshoot this, you have to verify the valve activation, so if it is working. So if you actually touch the valves, you can see that there's some kind of clicking. So if it is working, there's some kind of clicking on the valves. So you also inspect the wiring and the connections. So if it is the electrical system itself leading to the valves or the pressure sensor. And then there's battery failure. So of course, you find that the batteries have been removed by, now people have removed the batteries from the monitor. So that I think you can go a human error. But then there's, you can find that the battery has actually degraded and there's capacity degradation, so it's no longer able to store energy or to give out energy. And also, I can see the fault of the charging circuit failure, so it's no longer able to charge. The circuit itself is no longer able to supply power to the battery. So you can actually verify this by just attaching the power of the monitor. So you see that it's actually shut down immediately, or it takes a little time and then shuts down. So you know that the problem is the battery. So you have to troubleshoot this. You have to check the battery voltage, and also if it is actually damaged, you have to replace the damaged battery. And the last common fault that has been presented, has been presented in this presentation is actually the connector or internal module ports. So this is internal connectors or internal module ports. So this time we have now opened the monitor. So if you see on your in the picture, there's actually a VP module, NIVP module. Yeah, so that's the NIVP module. You can actually see the two pressure sensors, and this one, that's the SO2 module. So in monitors, we find that the PT module, the ECG module, what else of the monitor is actually monitoring. So you can find that there are ports with these modules or connectors that are going in the module. So you can see there are connectors going in the module there. So you can see bent or broken connector pins. Those are connectors that are bringing the modules. You can see loose internal cables or oxidation or contamination. I say that they form some kinds of blast. You can actually verify this by seeing actually the intermediate parameter readings and see that the accessories are not being designed. So for you to actually troubleshoot this is to inspect the connectors. You can actually inspect the virtually. You can see, then you can actually see is there any oxidation happening. You can actually clean the contacts if there is any oxidation. And you can also receive the internal cables that is removing and deconnecting these cables or the modules to ensure that there's proper electrical contact. So those are some of the common faults. There are a lot of faults that you have, and these are some of the common faults and how we can actually troubleshoot them. So I think this is the last slide in this presentation. I think I will then hand it over to Peter. All right. So thank you so much, engineers, for the wonderful presentation. Right now, I'll take questions and comments. So as I said earlier, we had questions in the chat. So I think now is the best time to take those questions. So we have, by the way, if you have any question or comments, you can just paste your question, comment in the chat, or you can raise up your hand as to read what's your. So in the chat, we had 2 more questions that were not covered in the first part of the presentation. So the first one was, how do you erase how do you get the NICT internal memory file which is full and not taking measurements? How do you do it? The NICT internal memory file full and not taking measurements? So I understand this question was asked by David, and I want it over to you engineer to take up that question, and then you can move on to the next question.
Can I take that question, Victor?
Yes,
All right. The method will depend on the type of patient monitor you have. But in general terms, the first step in most patient monitors, you select the menu button, or in some patient monitors, it's labeled patient set. So you navigate, after you've selected the menu, you navigate to patient setup. Then you have an option that is discharge patient. It can either be similar to a phrase like that. You'll be prompted because now it's like you're deleting the history. So you'll be prompted that, are you sure you want to do this? Then when you press OK to confirm, all the information that is stored by the monitor will be cleared. But if you have a specific device, maybe you can just let us know the name of that device. So I think for you, to help you properly, just visit us on BME Conza. We'll be able to help you properly if you have the make and model of the device. Over to you, Janet.
Yes, thank you, Kelvin. I just also wanted to add that I think the question was also talking about the NIBB machines. These are the small ones, not like the whole patient monitor. If you're using these ones, there are a few buttons over there. And normally you see an M or S button. M is for memory, S is sometimes for S. You can either have M or S. So when you long press either of these buttons based on the device that you're using, when you long press, it takes you to the memory of the device, and then you have the right to navigate through what you really need to erase through the navigation keys. There is some sort of buttons or keys there that you can just navigate through, and then you press OK, then you delete. Thank you.
All right. Thank you so much, Elias. I hope that answers your question. So the other question, I would not really say that the question is but I love that thing that someone has a problem because the monitor whose NHDP shows error problems. So before I ask any question to come in, maybe it will help for you just to give clarity. Anyway, for the one who posted this question, it will be easier for you just give insight in what error problems are you experiencing so that our presenters can actually write a problem and so that we get an answer. Otherwise, this is too complex because it's just saying there's a monitor whose NIBP shows error problems. If not, you can also just submit plans. For the meantime, if anyone with a question or a comment, just raise up your hands or paste it in the chat, and I will take your question. Thank you. There was also another question. It reads, how often is calibration required? How often is calibration required? So our engineers, you can take up the question. I see a hand from Janet.
All right. So normally you're supposed to be doing it annually, but some calibrations are device specific. If you check some devices or some models of patient monitors, they will specify in the service manual that you should be doing it annually or twice every year. I'll give an example. There is a certain model of TELUS they specify that you do it twice. Once every 2 years, like every 2 years. So that's the time that you're supposed to do the calibrations. But calibrations normally not another person can do. As long as you know how to calibrate, you can go along. Otherwise, they also do recommend that you could just contact the manufacturer because it needs you to have the passwords into the service system of the patient monitor. Otherwise, if you have access to the password, it allows you to do the calibration. Thank you.
All right. Thank you so much for that. At some point, I also saw a hand from Lloyd. I don't know if you still have anything to say. If you have, you can come in. If not, just give me a thumbs up.
Yeah, I think Janet has covered most of the things that I wanted to elaborate as well. So yeah.
All right. Thank you so much. Kenneth, if you are still here, just unmute yourself and speak. You have something to say.
Thank you. I hope I'm audible. Yes, I think my questions have been answered. However, I have a comment, and I was looking forward to, I don't know whether I came late, but I was looking forward to see a presentation for a 5 or 7 or more than 5 parameter patient monitor, and especially something taking CO2. So maybe next time we can also plan for that. I don't know whether I came late. I'm sorry for that. Maybe that presentation was done. But I'm looking forward to a discussion for multi-parameter, a bigger monitor with several parameters. Thank you.
All right. I see a hand from Janet.
Thank you. Of course, mine is just Charlie from Engineer Kenneth, and thanks for joining this call. So, area we have talked of. The first presenter actually pointed it out that there are so many accessories or probes where you can connect your patient monitors to. That's making it a multi-parameter. And normally you have the SpO2, you have the temperature probe or connection, you have the ECG, and you have the NIPB. That makes it 4. But I think your point was trying to point at having 5, which the 5th one should be the CO2, right?
Yes, true, please.
All right. So I think I can just pass it to Dominic. Dominic, do you have anything to say on CO2? Or although you also raised the hand, because I know that we didn't specifically talk about it, but I don't think the process is different. Maybe if you can have anything to just mention about it. Thank you.
All right. When I raised the hand, I wanted to comment that this presentation mainly focused on the machine itself, rather than the other parameters. But yeah, I think it's important that the CO2 also should be considered. Maybe the team can actually organize a special webinar that will actually tackle specifically on that CO2 devices. CO2 parameter. That's what I wanted to comment on.
All right. Thank you so much. Janice and Lloyd for those things. Other than that, there is no more question in this hands. So at this moment, I also want to point it out that for those of you who asked before the presentation materials and the session, so you can find the presentation materials and point it out in the daily for that. So either you can have an Android application or just listen to the document the web version of the app, so you can answer every presentation that you have had in the past, including this one. Yeah, and for the recorded session, it will be posted on the YouTube channel in the next 2 days. Otherwise, thank you for all your questions. And reaching this ends, I think we can end the session. I just want to extend my appreciation to each and everyone for joining us today. You have been a good audience, and thank you for your contribution as well. I also extend my appreciation to the engineers who were presenting today and those of you who are taking the questions and everything. Thank you so much. And I've seen you.